Today I want to talk about the next chapter, which is on classes. I think that's chapter 5, is that right? Chapter 5. All right, so oops. So what I'm going to do is take one of the problems that we worked on already and show how to re-express it using what are called classes. So I'll start up the solution that I've been using to store these problems. I think it's this one here. Not that one. So in this problem here, this was to simulate what's called a random walk. And so you have a starting point, and the program goes through steps, and at each step we randomly decide whether to step up, down, left, or right, or north, south, east, or west. And then we take that random step. And then we use this graphic representation just to see what it looks like when we step randomly in that way. It's called a random walk. So what I'm going to do today is to look at how we might be able to more easily manage the logic that this application is comprised of, using a programming pattern called classes and objects. So to do this, I'm going to create a new project, and we'll work in the new project. I'm going to call this I'm going to call it random walk. And we just have to remember how to go through the creation of this project. And we have to remember to turn off Unicode. And then in the, I think it's 326, is that it? Yeah. Then I'm going to copy the files that we need. There's 5 files. So I'll start with, basically I'm going to copy that random walk problem, P326. I'll copy the files for that and use those as a starting point. And one thing that I want to do is take out these horizontal lines. I don't think that adds much to the problem. So let's build and run this. Let's see if it builds. I'm going to set this as the startup project just to make it more convenient. Check, it's successfully built. Let's run that. Well, the other thing I want to do is take out the animation. This is which is this code in here. This is a little tricky. This is a hack that I put in there just to get an animation. But I'd like to take that out. That's it works differently on different systems. The author's library is not really meant for like a real-time simulation. So let's take that out. And then let's cut back on the number of steps we take. Let's take 10. There it is, 10 random steps. Actually, this is what I'd like to do. I'd like to draw a line that shows the step that we took. So here we have, so how are we going to do that? So we're going to draw our from our origin, we're going to take a step, and then we'll draw a line from our previous location to our new location. So that hopefully that'll help us see how the random walk is occurring without that animation built into there. So there's a problem we'll start with. So let's go ahead and do that. This is the first. And I'm going to call this, instead of drunkard, I'm going to call it walker. This is our walker. This is where we output the point. Actually, it's the walker location, right? It's the walker. We'll call it the walker. Walker is just a point. And then it looks like that. So let's do it like this. Let's take let's create another point and call it the previous step. And we're going to set it equal to the current step. Call it step. And I decide, I think it's better to use step actually. I'm going to change the name of that to step. Alright, so we have a step, and then we have a previous step. Maybe that's not good. Previous step, so that would be, no, change my mind again. We'll call that the walker. And this previous step, we'll set that equal to the walker. There we go. And then after we take a step, then we draw a line from our previous step to our current location called the walker. And then we have to update the previous step. Oh. What's that? Step. Oh, walker, sorry. Yeah, I see a problem actually with the terminal, my identifier names. The variable names are confusing, but let's try to clean those up as we go along. Let's see what it looks. There it goes. It looks like this. But why is this not shown, I wonder? Let's add a few more. Let's go 30 steps. I don't get it. Why is the last point not rendered? Oh, we never where do we actually display the, oh, here it is. So it's better to display the, see, the problem is this. First we display the walker, then we move the walker, and then we test to see if we're at 30. If we're at 30, we don't do anything, which means we don't display the last point that we calculated. So to fix that problem, we'd need to display the position after the move, but that means we wouldn't get the first position. So let's go ahead and display the first position as well here.
Sorry, I got here late, but which
Yeah.
problem were you doing that one?
What we're investigating now is some material in Chapter 5, which is on classes. And so what I want to do is take this random walk code or problem that we worked on before and redesign the solution so that it uses a class, hopefully to make the code easier to understand and extend and work with. I don't know if people followed that last. Do you see that problem? Why we weren't printing the last step? Because we were not displaying the point after moving. So the last move that we did caused us to exit the loop, so we never got to display the last point. Okay. Anyway, let's now. What I'll do is show you how to define what's called a class, and I'll explain about this as I go along. So as you read through the chapter talks about this, and you're going to need to study this chapter pretty carefully. Look at the code and the author's explanations. So a class is like a class is a data type, actually. It's called a user-defined data type. And it's like a pattern. Some people call it a cookie cutter. They compare it to a cookie cutter. It's not the cookie, it's the pattern that the cookie is made out of. So the class is a data type. It's like an int or a double. You know, a double is a data type. You might declare, variable x as type double, variable y as type double. So x and y are instances of that data type called double, or double. That's double is double precision floating point. And just like that, we can define our own data types using this syntax that I'm going to show you. And these data types are referred to as classes. So we're going to define a class, and then we're going to create instances of the class. So let's call the class walker. So it's a thing that does the walking. But the other kind of way that we could look at solving the problem is defining a class called step and thinking about solving the problem in terms of this abstraction called a step. So it's not always perfectly clear what you need to do to solve the problem. A lot of it has to do with style and just how you think through the problem. Now let's do it like this. Let's create something called a walker. Now this walker, it'll look something like this. We'll create an instance of the walker like this. And then we'll have a loop. And the loop runs exactly 30 times. And we'll tell the walker to take a step, a random step. Actually, it should be a verb, right? So we'll call them step. Step randomly. Just call it step. And then we're going to plot the we'll do it like this. We'll do display position. After we create the walker here, we're going to display the position. Then we're going to take 30 random steps. After each random step, we're going to display the walker's position. Now this code here is sufficient to solve the problem, as long as we implement this class called walker. So this code is a lot easier to look at than this code down here. That's one of the reasons why we use classes. Alright, now as you can see, this is not building now. Display position. When we do walker.display position, it means that there's a function called display position that's defined in this walker class. Let's define those. There's something called a public interface and a private. So public member variables, public member functions, and then there's private member functions and variables as well. Talk about that a little more later. And so we have a function called display position. That returns a void. And we have another function called step that also returns a void. As you can see, that now the compiler is not reporting a syntax error anymore, because we've stated that display position and step are in fact member variables of this walker data type or walker class. You know, I'm going to take this code out here because that's not building, because I'm reusing that variable called walker. But the thing is, we haven't implemented display position, and we have not implemented step, and so we can build. No, we can't build. We can compile, but we can't do what's called linking. There's the build process is comprised roughly of two steps. One is to generate machine code from the source code and store it in these files called object files. Now, normally a program is very large. Okay, the programs aren't normally small like the programs we look at. Like Microsoft Windows, okay, that's a program. Microsoft Windows is more than 10 million lines of code. You know, the most recent version. 10 million lines of code. You know, compare that to the programs we're looking at. That's a big program. So, you know, like your browser, like a Firefox browser, that's a program. And that has got a lot of lines of code. I wonder how big Firefox is. Does anyone know how to get this? $2 million? Oh, here. 2 million lines of code. Wow. Huh? 2 million lines of code changes. Well, that must be over several changes. Anyway, but they're big. You know, we don't really care. It's, you know, 500,000, a million, 10 million. That's all pretty much the same. Okay. So the idea is that when you compile an individual, this is called a compilation unit, this source file, and that file is then translated into machine code and stored in another file, a temporary file called object file. And then the next step is to link the object files together so that in one file you've got code calling a function, but the function exists in another object file. The compiler didn't know that. When the compiler went to generate the object file, it's saying, well, yeah, I'm going to call a function here, but I don't have the implementation of that function locally in this file. It's somewhere, it's in another object file. But it's been declared as existing here. Here we've declared the functions as existing, but we haven't provided the implementation. And so the compiler says, yeah, I'll create the machine code for you, but I won't resolve. I'll put in stubs for calling the functions, which are you told me are defined somewhere else. And then it goes to the next phase, which is to link it all together. So it goes through these object files and tries to resolve these function calls. And that's where this will fail. So this will fail to build, not because there's a syntax error, not because there's a linkage error. It cannot find the display position code. Here, let's see how that works. I'm going to build. One failed. Let's look at the failure. Unresolved external symbol. Step. Unresolved external symbol. Display position. So this linkage phase of compilation is trying to go in that phase. It was trying to find the location of these external symbols. So an external symbol can represent a function that you have to call into, or it can represent a variable or storage location that you need to access, read, or write into. So there's two types of external symbols. So let's go ahead and provide an implementation for these functions. And there's many ways to do that. One way is to do it like this. We could do it inline, right inside the class declaration. We just put implementations. You remember, when you define a function, you have an open bracket with lines of code and then a closed bracket. Well, we can do that here, but we have nothing inside. So now this will build. 1 succeeded, 0 failed. So that'll build, but it doesn't do what we need it to do. And the way I'm going to show you this way. Another way to do it is to define these outside of the class declaration. And this is the syntax. You make them look like regular functions. We're almost there. It's not good enough. See, right now this display position is called a global function. It's not part of the class. It's not part of the data type walker. So we have to tell it that it's inside the data type walker. So we do it with this syntax here. Use the name of the class followed by 2 colons in front of the function name. Now, once again, this will build. This is equivalent to the last version that I showed you. Well, it does nothing. It builds, but it does nothing. Let's go ahead and let's start doing something. Let's display the position. So when we display the position, we're going to do something like output the CWin, right? Some kind of a point. Well, where's the point? Well, so we need to keep track of the position of the walker. And we do that by using a variable inside the class. And this variable, we're going to make it private so people on the outside, code on the outside of the class can't access it. It's hidden away. It's part of our internal implementation. And that's why we declare private. The functions that are public, that's like, okay, code on the outside of Walker can call those functions because they're public. But point, that's a hidden data member. Code on the outside of the class cannot access or reference that hidden data member. And this is a typical organization of a class. Because we could have put this, we could have put the point up here in the public section. That's fine. But it goes against the common practice, which is to hide your internal state from the outside and expose only the minimum functionality that you need to expose. So now we're at least we're displaying something here. We've got a point. Of course, we call step, and we're doing this 30 times. So when we call step, we do nothing. So what we need to do actually is move this point around. So let's do it. We're just going to grab this this business here. Here's the step function. Something didn't, forgot this. Oh no, we don't want it in a loop. The loop is on the outside. We don't need the loop. Control KF, that's to format everything automatically. And this Walker is not, and you know, I don't like position here. I don't like point. I'm going to call it position because that's a better variable name because of the look at the this function called display position. You know, we have a function called display position, a data member that we operate on is called point. And it's better to name it position, so it corresponds to the function name display position. So, you know, if you spend time working out naming in your programs, they become much easier to build and to maintain. There it is. Let's see, what do we do here? So when we step, we generate a random integer between 0 and 3 inclusive. So we take a random integer called rand, which is some number between 0 and a large value, divide by 4, throw away the quotient, and take the remainder. That's what this percent sign does. By the way, there's one of these on the midterm. So make sure you know what that operator does. It's just a remainder. Called a modulo operator, or you could call it the remainder operator. So there it is. Now, of course, we don't have the line, but we've got the random stepping now. So here, and I'm just going to delete this old code. We don't need this old code, except we're going to need one of these in here, and that's this. I'll explain in a minute why we want to use that, and I'll put it up here for now. I'll leave it commented out. I'm going to talk about that one in a minute. So we have replaced this stuff. Now look at how much more compact our logic is. We create a Walker. We display its position, and it has a default position. We display its position. And then we execute the following two lines 30 times. We take a step and we display the position. You see how much easier that is to look at? That's why these big systems can happen. You can't create a program with 2 million lines of code unless you have some organization skills, unless you have nice, like, standard patterns and approaches to organizing logic or algorithms. So classes is a technique of organizing logic that was not originally used when computers were first built. When computers were first built, there were conditionals, there were loops, and that was it. Then they invented functions, and that helped a lot organizing code, so they could break it into these functions. And then, then there are other constructs, but mainly the next evolution was the invention of what are called classes or object-oriented programming. So most code these days is built using an object-oriented architecture. That's what we're looking at. So let's get the line in there. How do we display the line? Well, that's a thing. When we it's not always clear where to put things. Okay, so we want to draw a line. When the walker takes a step, we want to draw a line from where the walker was to where the walker now is. Do we want to do the line drawing inside main in this loop here somehow? Or do we want to incorporate the drawing of the line inside display position? Or perhaps when we call, so that's the question. Do we want to put the drawing of the line, do we want to embed it inside of one or both of these methods or functions? Or do we want to code up the drawing of the line outside of the walker class and put it inside main? This is a typical design decision that people have when they are writing programs. Anybody have an opinion? Inside the walker class? Yeah, that's where I would like to put it. One disadvantage with that is that the word display position is not as precise, because we're displaying our position, but we're also displaying where we came from. So it's like display our step, display position and how we got there. So it's now the precision of the term is getting a little fuzzy and weak. So those are the kind of things you have to think about when you write programs. Well, let's go ahead and put it in there. So let's so when we take we're going to need something like a previous position. Yeah, I'm not sure exactly how to do this, but let's go ahead and investigate. We have a previous position, and when we take a step, before we take the step, let's preserve our current position inside previous position. Previous equals our current position. So that's not remember, that's not equals. I say equal, but it's not equals. This is, how do we read that symbol? When we look at the symbol, we should think assignment. Position is being assigned to previous position. And then inside step, inside display position, we can then draw the line from the previous to the current position. All right, now we have it. By putting it inside the class, we get to keep this code inside main smaller. And that would be my tendency. I would tend to try to hide the detail, the messy complexity inside of the class, and keep the higher level code simpler. Now, I want to talk a little bit more now about how to organize this. Normally, well, see, the standard approach is to create separate files to store the pieces of your program in. And a common organization would be to create one file for every class, or two files for every class. One called the header file, which is the interface for the class. The other file is called the implementation. Let's go ahead and do that. And the book talks about this. All right, let's add a new item. We can add a class, and it generates both things for us. I'm going to do it manually by creating a new item. And this will be code. It's a C++ file. We're going to call it Walker. Notice I use uppercase W. That's because my class name is an uppercase W. Although that's just a convention. It's not a requirement. And so there's walker.cpp. Now I'm going to create another file. And this is called a header file. So an implementation file ends with the extension .cpp. The header file ends with the extension .h. And then what we do is this here. I'm going to cut this. This definition or declaration of the Walker class is put in what's called the header file, the file that ends with the extension .h. And the implementation of the functions in that class are put in the .cpp file. But now that has broken the program. So let's go ahead and fix that. First of all, Walker is no longer defined. The compiler doesn't automatically go out and get the header file and use it. So we have to include. That's what the include statements are for. So we include walker.h. Now the build error has disappeared because the compiler is saying, oh, okay, you want me to take the declarations that are in walker.h and use those to resolve the symbols that you're using in this file. So it accepts that and it uses it. Now main is building. So the object file for main can be built. Now, Walker, the problem with walker.cpp is Walker is also undefined. So to do the same thing in walker.cpp, we need to include the header file. And now Walker is defined, but look, line and cwin is not. Because line and cwin are defined in this header file, or the header files that header file includes recursively. So I have to carry that over as well. Oh, now the symbol Walker is defined in there, so that's no longer underlined. The symbol CWin and the symbol line are defined in this header file, and therefore there's no longer a syntax error being reported on that either. So there is no more syntax errors. Let's build. It failed. What's that?
In the walker.cpp file, we are using random.
Oh, that's right. Here. Doesn't seem to be a problem. Oh, point. See, point is defined in here. See, this file should be in here. As we're using point in here, so we need to include that here. Although it wasn't necessary to do the build. Let's look at the error messages. There's a missing oh yeah, so point is not defined here. Alright. So that was it. The problem was this. That was missing. But this rand, it must have come in through here. Let's see. Like we can see that the compiler or the Visual Studio is showing us how the function is declared. If we right click and then go to, say, declaration, it shows us the header file that it's defined in. You see how it opened up the header file for us? So these header files come with Visual Studio, or if you're using another compiler, there'll be header files that come with that compiler, like in Linux. They have a separate set of header files. And this is the declaration of the function. It doesn't show the implementation, it's just the declaration. So rand is, it takes no arguments. Look at all these modifiers that specify how this rand function is going to be used in your code and constructed. I'm not going to get into those. And you'll notice because we include Walker here, we don't need to include this file anymore because Walker includes that file here. But it doesn't hurt to be redundant. Why doesn't it hurt to be redundant? I'll show you why. I opened up CCC MSW.h, and this is the reason it doesn't hurt to be redundant, because of this little bit of code called a compiler or a pre-processing directive. So it says if this identifier is not defined, so if ndef, that's if not defined, if this identifier CCC underscore MSWH is not defined, then do the following. So this is the beginning of a conditional if block. All of this is inside the if block, and at the very end we close the if block with an end if. So if this identifier is not defined, then include everything inside of it. This is called a pre-processing directive. It's done before the actual it's the beginning phase of compilation. What's the first thing we do if CCC MSWH is not defined? The first thing we do is we define it. So the next time we try to include this header file, we don't redundantly include the same declarations. And we have that problem right now. So if we were to, say, include somehow include the Walker file twice, maybe through some kind of an indirect route by including another header file that includes Walker. We end up trying to include the Walker file twice, and we're going to get a compilation error. Let's see. So right now we cannot include this twice. But so let's add that code. Looks like this. Oops. We'll follow the same convention here. If we're going to call it Walker underscore H. If Walker underscore H is not defined, then let's define it. And then let's end the if block there. Now look at main. Now if we end up trying to include the Walker file twice, it's okay, because of that extra precaution that we included in the header file. So in general, although for our particular problem we don't need to do that, but in general it's good to get into the habit of sandwiching your declarations in header files with that this if and def preprocessing directive that ensures that the header file is only inserted once. Okay. Now the issue now, well, it's a small issue, and I just wanted to talk about why I'm using srand. Look, if we run the code, every time we run it, we get exactly the same pattern. That's because rand is a pseudo random number generator. So it will produce the same string of integers each time you call it, each time you start calling it, unless you reseed it. So S stands for seed. So we want to seed the random number generator with a value. And the value that we seed it with is the value returned by time. The time I think is, I think it's a long. Let's see, does that build? That's right. So just to make this easier to look at, we use the current time. When we go time 0, we're saying give me the number of seconds that have elapsed since the first second of January 1, 1970. That's how time is implemented. So this gives us the number of seconds since 1970. And so we use that. That number is going to be changing for us pretty much every time we run the code, unless we run it within the same second. So we end up putting a different seed into the random number generator each time we run the program. That gives us the variation in patterns. So there's a new pattern. There's a new pattern. There's a new pattern. Any questions at this point before I move forward? I pretty much gave you a lot of it. I gave you the full, this is it. I mean, this is it. I'm not going to talk about, well, a few more new things, but essentially the hard part of understanding this chapter I've just gone through. Right, that's it in a nutshell. And also how to use it. And there's some other details that you need to learn about, things like overloading. The book has a section on overloading. And let me talk about overloading now. Do you all feel overloaded? Just kidding. That's stupid. So here is, we have something called a constructor. So right now, when the compiler constructs this data type called walker, it generates some default initialization code. So when you create an instance of walker, which is done here, when you create an instance of walker, some initialization has to be done. And we can, right now we're relying on the default initialization that the compiler generates for us, but we can override the default, and let's go ahead and do that. So we do that by declaring what's called a constructor. And a constructor always has the same name as the name of the class. This is true for many computer languages: Java, C#, C++, and a long list, but not for all of them. Like Python, for instance, the name of the constructor is not the name of the class itself. So so the constructor looks like a function, but it doesn't have a return type. So you don't say void walker, you don't say int walker. The constructor will never return anything. It's a function body that contains initialization code. It runs when the system allocates a new instance of the class. So let's go ahead and implement that. So we do it like this. It's the same. It looks very similar to a function. Essentially is a function, but as you can see, we omit the return type. So let's play with this initialization. Let's suppose instead of using the default value for point, that we give it an alternative starting position. Let's put it at 5,5. Now I'll put it at 7,7 just to make it more visible. So when the system creates the position object, it runs the constructor for the position object, the default constructor, which sets its position at 0, 0. So we're overriding that. Oh, something looks bad. What happened? So why is the previous position? So this is position. You know what it is? We have to do this too. We have to also set the previous position. Looks like that. So we're going off the side of the screen there. So that's called a constructor. A constructor is just a function that's not run when an instance of the data type is created. And you can what's called overload functions. So we can have an alternative version of the constructor. Perhaps that takes a point. So we give it a different initial position. So we have one constructor that has a default that assigns a default position to a walker, and then we have another constructor that assigns some specified initial position to an instance of the walker. So we're going to need to implement that. You know what? I better do it like this. This is the initial position. Let's do it like this. So now when we create an instance of the class, we give it the position passed in. All right, let's take this out. Let's see if that builds. So I took out that special initialization, so the default constructor is now being used. Let's use the alternative constructor. How do we use the alternative constructor? Exactly, pass in the point that we want. So this will be, say, 7 comma minus 4, just to give it something else. There it is. So now we have two constructors. Just to go a little farther, let's go. Let's create two versions of. Nah, not going to bother. But you can create different versions of the functions as well. They're also called overloaded. The compiler distinguishes between two different versions of a function, two different versions of a function by its arguments. It's the same function. In this case, it's the constructor function. But there's two implementations of it, which are distinguished by looking at the arguments that are being passed in. So when the compiler sees this, it says, "Oh, I need to run the version of the constructor that takes a point as an argument." Well, it doesn't run the default constructor. I have some other thing in mind. I was, when I got up this morning and I was thinking what I was going to talk about, and I looked through our problems and I found this one, and I thought this would be fun to work on. And I had this idea that we could simulate the stock market if we start the walk from the side of the graph. If you start the walk from here, and then always step to the right one, but then randomly step up or down, then we're going to get some kind of a random walk. It'll look like a stock market chart. So I was thinking about doing that, and we can do that, but I don't want to overload everybody, so I'm going to stop here and just leave it at this. Is there any questions about this or anything else that we're working on? No? Okay. Well, then that's it for today.